So goal number 5 in our course is what we're going to turn to next, and our last one for today. The goal is going to be to choose a strategy and implement it to solve a system of two equations, specifically two linear equations. And so we've built this skill up kind of as follows. When we first met this skill at the beginner level, what we talked about at the beginner level was just a sense of what it means to be a solution of a system of equations to begin with. And at the beginner level, we did some graphing, graph it to solve it. And that's always an option. It's just kind of a burdensome option because it's going to require you to go back into each of these two equations and rearrange it to solve it for y, for example, and then from the slope and the intercept of those lines, we can sketch them and then try and read the coordinate of their point of intersection off of a graph. So it's labor intensive, but it gives us a good intuition for what we're really doing when we're solving one of these systems. At the intermediate level, we got down into the nuts and bolts of the algebra, and we developed a method that we call the method of substitution. And that's kind of a good second level skill, because if we know how to do the beginner level, we're going to have to, as part of our beginner level skill here, rearrange at least one of these equations to get the y by itself. Well, once we've rearranged one of these equations to get the y by itself, we can plug that expression into the other one and give us a single variable equation that we can then solve to get our ball rolling. Today we're going to forge to the advanced level of skill. And this is a way that is just sort of a different approach to solving a system that doesn't involve substitution, but instead involves a process we like to call elimination. So it's the elimination method. And then as part of this advanced level skill, we also today want to ask the question about what, if anything, can go wrong. So there's a particular thing that can happen when you're solving a linear system that can make your solution unlike the other kinds of solutions that we run across. So I'm hoping that we get a chance today to talk a little bit about both the elimination method and also kind of look at these weird oddball cases for things that could happen that are unexpected, and we'll talk about how to interpret them. But let's start by going back real quickly to the how do we use a graph to solve a system of equations. So what I'll do is I'm going to take this system right here and just take one of the equations, just for kicks. I don't know if I'll do this for both, but let's take the first one. And let's rearrange this equation to solve it for y. This is a skill from goal number 2 of our course, to solve for one variable in terms of the others. So if I want to solve that red equation up there for y, what kind of steps can I follow? What should I do first? I get the y by itself. Great. Let's start by subtracting 3x from both sides. Again, we're working the order of operations backwards, so we'll do all the addition and subtraction that we can on the left-hand side first. Okay? And now that all the addition and subtraction from my left-hand side is done, what do I do to get that y alone? Divide it by -5. So I'll divide both sides of this equation by -5. And I'll get an equation that looks like y equals -1 divided by -5, otherwise known as 1/5. And then -3x divided by -5 is otherwise known as positive 3/5 x. So one way that we have of approaching a problem like this is just to take our original equation, or maybe both of our original equations, and rearrange them to isolate the y. So here, that would give me y equals 1/5 plus 3/5 x. Approaching the problem this way, if we know enough about these equations to then generate a graph of them, then where do I find the solution of this linear system of equations on this graph? What point am I looking for? I'm looking for the point where they intersect. And according to my nifty graphing tool, which you can use at home if you want to do this kind of thing, this is desmos.com. According to my little tool, -2, -1 is the intersection point for these two lines. So we interpret that to mean that the solution of this system of equations is x equals -2, y equals -1. So that's if we have a nice accurate graph and a way to know that our intersection is exactly what it looks like on the graph, then we can use this method. Because our graphs can only be so precise, it's only as precise as our eyes or the resolution of the computer screen or ink on page, we can get kind of a rough sense of what the intersection should be. But if we want to get to the level of precision that mathematics demands, we should have a way of approaching this with algebra. And that's where the substitution method comes in. So this is the method that we developed a few weeks ago, the last time we saw this material, whereby we can solve this system of equations using algebra by doing what? Because one of my equations has the y by itself, what does that allow me to do to get the y's eliminated from my second equation? Where this method gets its name is from the step of taking the y in the second equation and replacing it, substituting it, by this quantity with x's in it that we know y must be equal to at that point of intersection. So 1/5 plus 3/5 x, we're just going to drop it right in the second equation where the y used to be. And when we do that, our y's are gone from the second equation, and in their place, we have this expression with only x's in it, 1/5 plus 3/5 x. So now we have an equation that we can solve. I've got a 16 from the right-hand side there. There we go. We have an equation that we can solve for x. Now is a good time to remind yourself, what's a great strategy that we can use to get rid of the fractions in this equation? Let's clear those denominators. How can I clear the denominators in this expression? What should I do on both sides? What should I multiply by? Let's multiply by 5 on both sides of this equation. So I'll multiply this by 5, I'll multiply that by 5. That will get rid of my fractions so that we can deal just in whole numbers. Don't forget, though, that when we do that, we have to distribute. This multiplication by 5 distributes to every one of the terms inside of my brackets, so that what I'll end up with is 5 times -7x will be -35x, minus 2, and I didn't do this distribution. I probably should have done the distribution first, but I'm going to skip that step for now. 5 times 1/5 is going to give me 1. You can check this fraction arithmetic later if you like. 5 times 3/5 is going to give me 3. And then on the right-hand side, I have 16 times 5, which is 80. Now, since all I have are whole numbers, I can carry out my distribution without worrying about any fraction arithmetic. That's going to give me on the left-hand side -35x minus 2 minus 6x equals 80. -35x minus 6x, -41x minus 2. Because now to get the x by itself, I need to add 2 to both sides. -41x equals 82. And then to get the x finally alone, I'll divide by -41. And sure enough, that gives me an x value of -2. But don't celebrate just yet, because having an x value is not enough. What else do we need? We need the y value. So what we'll do is take that x value and do what with it? Where? Yeah, go back to the original equation. You can use whichever one of them you like, and just substitute the x back in. So my original first equation was y equals 1/5 plus 3/5 x. So I'll substitute the x that we know now back into that original equation. And do out the arithmetic to find out y. 3/5 times -2 is -6/5. 1/5 minus 6/5 is -5/5, otherwise known as -1. And sure enough, we have now the algebraic verification that the graphical solution that we saw on the graph a moment ago is actually precisely the solution of this system of equations. So the arc of the substitution method is that if we happen to know what one of the variables is explicitly in terms of the other, as we did right here, we can plug that expression into the other equation in place of that variable and reduce to an equation with only a single variable in it, which we can solve using the techniques that we know for how to solve a linear equation. Once we find the value of that first variable, plug it back into one of the original equations, and it doesn't matter which, to find the value of the other. Now, it turns out that this original system wasn't particularly well set up in the beginning for the substitution method. Because if you remember, we did a little bit of work to change the original system into this form because we were looking to graph it. The original system, in fact, came to us in a form where the y wasn't solved for by itself on one side of the equation. Instead, it looked like this, right? Where the x's and the y's were both entangled together on the same side of both equations. So our advanced technique for today is a method called the elimination method that's going to let us use these equations as they are without solving for one variable in terms of the other. You always have the option to take the substitution method. That's fine. You can always use it. But in an example like this, it has the overhead of then having to solve for one of those equations in terms of the other first. Right? So that's the price you pay in order to use the substitution method in a problem like this. If you don't want to take that route, if you don't want to solve for one equation and one variable in terms of the other first, the elimination method gives us a way of doing that. And the basis of the elimination method is something that I saw some people attempting on the most recent attempt at the exam, with mixed degrees of success. So let's try and iron it out here. The basic strategy is that we want to take these equations and just add them together in some way. So combine the left-hand sides of the equation by adding, combine the right-hand sides of these two equations by adding. And if I just do that, then on the right-hand side, negative 1 plus 16 is going to give me 15. On the left-hand side, I'm going to get some like terms combining. My 3x and my negative 7x combine to give me negative 4x. And the negative 5y and the negative 2y are going to combine together to give me negative 7y. Now that's great. So by adding these two equations together, I get a new equation. And this new equation, if I combine it with any one of the two original equations, that new system is going to give me the same solutions as my original system did. The problem, though, is that we didn't actually do something helpful here. By adding these two equations together, we got a new equation that still had two variables in it. And so we can't really do anything with this new equation that we just found. It doesn't make it wrong, it just makes it unhelpful. What I would prefer to happen is I would prefer to add together two equations that result in the disappearance of one variable. If I can make that happen, then my result is going to be an equation with only one variable in it that then I know how to solve. Right? So we want to get back to that point that we were in. We want to get back to the point that we got to right here, where once we did a strategy of substitution in this example, we no longer had x's and y's, we just had x's. Because once we got there, we knew what to do. And as soon as I have the solution of that equation for x, then I can plug it back in and find a number for y, and then we were done. So that's the situation we want to find ourselves back in. Simply adding the two equations together didn't do it. Right? We still had an x and a y in our equation. So in the elimination method, the first step before adding is we want to pick one of the variables for elimination. We want to pick the variable that we want to get rid of. We want it to disappear. Generally, it doesn't matter which one of the two variables we pick. Let's pick y. For example, let's suppose that I want to make my y's disappear. And I want to make them disappear in the process of adding my two equations together. But I can't do that with a minus 5y and a minus 2y because those are going to add together to give me minus 7. So what I need to do is I need to change these equations first in a way that's going to give me coefficients of y that will cancel when I add them together. So I don't want to add first. Instead, what I want to do is first multiply. Multiply each equation on both sides. And I want to do so in a way that gives me equal and opposite coefficients on whichever variable that I'm trying to get rid of. Equal and opposite coefficients. Let's say for y. if I'm targeting y for elimination. So I guess here's my question. Is there a number that I can multiply 5 by and a number that I can multiply 2 by that will make the resulting products have equal value? We might be thinking about a number that we can bring 5 and 2 up to, which is a common multiple of both 5 and 2. What's the common multiple of both 5 and 2? 10. So let's set that as our target. Let's try and manipulate these two equations so that the coefficient of y is 10 in both cases. In my first instance, what should I multiply that equation by? What should I multiply the first equation by to give me a coefficient of 10 on my y? Let's multiply the first equation by 2. And if I do that on both sides, then my left-hand side is going to be 6x minus 10y, and my right-hand side is going to be negative 2. How about for the second equation? What should I multiply by in order to get my coefficient of y to be 10? Let's multiply it by 5. So I multiply my second equation by 5. There we go, multiply by 5. And then that's going to give me negative 7 times 5, negative 35x, minus 10y, and then 16 times 5 is going to give me 80. Okay, great. We're almost there, because now the coefficients of y are equal. But if I add them together, they're not going to become 0, which is what I want. If I add these two together, I'm going to get negative 20. So in addition to having equal value, I also want them to have opposite signs. So I'd like for one of these to be positive 10 and the other one to be negative 10. How could I fix that? How could I retcon it so that they have opposite signs? Yeah, right. Let's take one of the two multiplications that we did and make it a multiplication by a negative instead. So if instead I'd multiplied that second equation by negative 5, then my coefficient of x will become positive 35. My coefficient of y will become positive 10. And my 80 on the right-hand side will become negative 80. And now we are right where we want to be, because the coefficients of my y's are equal and opposite to one another, plus 10 and minus 10. That's great. That's a perfect setup. And we had to work to get there. Right? That was the overhead for using the elimination method. This is the step that's the trickiest one. It takes the most practice to develop. Okay? But if you can get here, it's basically, notice, it's basically the same thing that we do when we're thinking about finding a common denominator for fractions. Right? It's that very same part of your brain that you're engaging. It's the same skill. But if we can get there, then what's going to happen when I add these two equations together? Let's take the right-hand side. Negative 2 minus 80. Negative 82. How many x's am I going to have? I'm going to have a single term with an x in it, and the coefficient will be 35 and 6 is going to give me 41. So that's how many x's I have. That's the constant on the other side. But importantly, what's going to happen with my y's? Gone. They're gone. I'm going to have 0 y's. And another way to say that we have 0 y's is to say nothing at all. And that was the whole point, right? When my coefficients are equal and opposite and I add them together, my term becomes an additive 0. And now all we have to do is discover x by dividing by 41. And lo and behold, there's x equals negative 2. That was the x value that we found before. And as soon as I know a value for x, I can plug that value back into any one of my original equations. Let's suppose I take my first equation, 3x minus 5y equals negative 1, and evaluate that for x equals negative 2. So it's negative 6 minus 5y equals negative 1. Solve this for y, which I'm going to kind of burn through here real quick, adding 6 to both sides. So we get negative 5y equals 5, and then dividing both sides by negative 5 to get our y value, y equals negative 1, which also agrees with the solution that we got doing it the substitution way. Right? So one of the real advantages of elimination is that at no point in this process did we have to do fraction arithmetic. Whereas if we get a system that's not set up for substitution, the first thing that we did when our system was not set up for substitution was we rearranged one of the equations to get y by itself, and then suddenly we had a 1/5 and a 3/5 in our lives. Right? So if you don't like that, and you have every reason not to, elimination is a way of circumventing the fraction arithmetic, but it comes at the cost of doing this first step to balance the coefficients of whichever variable that you want to go away when you add the two equations together. But then once you do that, from there out, the method looks pretty elegant, right? Immediately, my y's are gone. I only have an x, and I only have one operation of algebra to do to solve for x. And then plugging that x back into any one of my original equations, I just have some simple whole number arithmetic to do to get me to my solution for y. Let's talk about that what can go wrong question. Going back to our graph for a minute. How many solutions did this system of equation have? In other words, how many times did these two lines intersect one another? Once, right? This particular pair of two lines intersected each other only in one place, -2, -1. So here's our original system again. And we decided that there is only one point that these two lines cross one another. And then my question to you is, why isn't that always the case? How do we have a pair of lines that don't cross in one place? Yeah, this is a thing we talked about 20 minutes ago, right? Two parallel lines do not cross each other in one place. In fact, they cross each other in no places. Right? As long as they are different lines from one another, they cross each other in no place. So the question here is, how do we connect that with the algebra that relates these two equations together? So here's one way of doing it. Let me dial my A, dial my A in to, I don't know, 6. And let me dial my B into -10. Okay, so maybe I won't have 16 here. Maybe I'll put this at -20. Okay, great. So now I've changed around the coefficients in my equation so that the equation I'm actually looking at now, my first equation is still the same, 3x minus 5y equals -1. But now my second equation has new coefficients in it. I'm just going to write them down here so that we can look at them together. My new equation is 6x minus 10y equals -20. So that's the blue line, and then the red line is my original. And these two lines are now, on the graph at least, it looks like they're parallel. If we wanted to, we could solve each one of these equations for y. I'm just going to do it skipping all the steps. So feel free to recreate these steps for yourself at home if you like. But this was the equation which we already solved for y a little while ago. And then this is going to give me y equals 3/5 x plus 2. Okay. So if I solve for y in both of these equations, this is what I would get. How can I tell from their equation that these two are parallel lines? This is the red one, or this is the blue one, rather, and this is the red one. How can I tell that these two are parallel, just looking at their equation? The 3/5 shows up in both equations playing the same role. What role is 3/5 playing here? What is it? It's the slope of these two equations. So these two equations have the same slope. Therefore, these two lines are parallel on the graph. Awesome. So then the question for us is, how many places do these two lines intersect? Never. They don't. And so what's going to happen if I try to solve this system of equations using the techniques that we learned today? We're not going to find a solution, but not finding a solution might not look the way that you think it looks. So let's try it. Let's try applying the elimination method to this system, and then we'll see when the bottom falls out of our solution process. So I can't add these two equations together yet, because I want to set them up so that, let's say, so that the y's cancel again. What should I do to these two equations to make it so that the y's are going to cancel? Let's find a common denominator, a common coefficient that we can bring both of these equations into, between -5, the coefficient of the first equation, and -10, or let's just say 5 and 10. So what's a common multiple of 5 and 10 that I can use as the coefficient for y?
10.
How about 10? So in order to get this first equation to have a coefficient of 10 on the y, what should I do with it? Multiply it by 2. If I multiply it by 2, I'm going to get 6x minus 10y equals -2. So now I have equal coefficients on my y's. If I want them to be equal and opposite, what should I do?
Multiply the next one by -5.
Yeah, I can multiply the second equation by, actually it could be even simpler. We could just multiply it by -1.
Oh,
Right.
-1, yeah.
That will flip all the signs on my second equation. Multiply by -1. so that this will be negative 6x plus 10y equals positive 20. And then, now that my coefficients of y are equal and opposite, we are set up to eliminate. So if I add these two equations together, what am I going to get on my right-hand side? Negative 2 plus 20. 18.
Eliminating the x and the y.
Yeah, that's exactly what happens. So not only does my y go away, my x goes away. And that's a problem, right? That's our big red flag. This left-hand side of the equation becomes 0. And so that right there is how we know that that something is afoot here. That's my little red flag flapping in the breeze here, right? Both of our variables are gone. And that means that whatever equation that we get here is either going to be true no matter what x and y are, or false no matter what x and y are. X and y have no ability to influence the truth of this equation. And our equation says that 0 is equal to 18. What do we think of that? Do the thing that CNN did on a presidential chyron a while back. It's not parenthetical. Right? 0 is not, in fact, equal to 18. But in order for there to be a place where these two lines intersect, 0 has to be equal to 18. But it's not. Therefore, how do we conclude? We conclude that this system of equations has no solution. So whenever all of your variables disappear and you're left with something false, that means that our system has no solution. It's not possible to satisfy this equation with this pair of equations with the same x and y. And so graphically, the picture is that we have two parallel lines that have no points in common. The last way in which things can go wrong also has to do with two lines that are parallel. And it also has to do with mathematicians being fussy. So when a mathematician says that two lines that are parallel do not intersect, there's a word that they're forgetting to use. They're forgetting to use the word distinct. Two lines that have the same slope, we decided today, are parallel. But what happens if those two lines lie right on top of one another? So if they're not two different lines, they just happen to have the same slope. And so they're parallel, but they're not different. They lie right on top of one another. In how many places does my red line intersect my blue line now? Infinitely many places. Yeah, exactly. And so in this example now, we have a pair of equations that have infinitely many points of intersection. My second equation is now 6x minus 10y equals negative 2. So let's take a moment and recreate the algebra that we would see if, again, we tried to approach this system, not knowing what its graph looked like, if we had tried to approach this system with elimination. We would have, just as before, multiplied the first equation by 2 and the second equation by negative 1. And we would end up with equal and opposite coefficients on my y, 6x minus 10y equals negative 1, and negative 6x plus 10y equals, I'm sorry, not negative 1, negative 2. And negative 6x plus 10y equals positive 2. When I add those two equations together, my x's and my y's are going to all disappear, which is, again, that big red flag, right? But what's going to happen on the right-hand side? It disappears too. So this time we get a red flag, but what do we conclude about the equation that remains? Yeah. 0 equals 0 is a true statement regardless of what x and y are. True for all x and y. And the meaning of that is that any x and y that satisfies one of these equations is also automatically going to satisfy the other. Why? Because on the graph, these two lines are right on top of one another. Right? So every point that lies on one of those lines also lies on the other one. And so we say that this system has infinitely many solutions. Because there are infinitely many points on each of these lines, and every point which is on one is also on the other, making it a solution of the system.